Yeah, the molecule of energy is ATP. And it's really a wonder molecule. But why is that? What is it about ATP that makes it so special? It's quite remarkable. And energy in particular is a very big topic in the health sciences, particularly in nutrition, of course. And all kinds of uh, diets have come around that claim to be like the wonder diet. Whereas really, dieting is quite simple. It's a matter of balancing your macromolecules, which is what we're going to talk about today, largely macromolecules. So I had some funnies up here that I think are kind of cute. This means you are acute as an acute angle, T as in tea pie, you're a cutie pie. This is chemistry humor. These are vegan witches. Yeah, I have potato here, of course, head of lettuce. And above all, these days, you know, because we're going through, well, a crisis, the pandemic, be nice. Be nice to everybody around you. So, okay, work and energy. There's different kinds of energy. There's kinetic energy, there's potential energy, there's electrochemical energy. So let's get a handle on what energy actually is before I delve into potential energy. Would anybody like to offer an explanation of what energy is? How would you describe it? It's the capacity to do something. What is it the capacity to do? Energy. I have a new message. Work. Good. Yes, energy is the capacity to do work. It's as simple as that. So kinetic energy is the energy of movement. And we saw last time when we talked about chemistry that molecules move all the time. Potential energy is energy due to an object's location or state. So when we look at a dam like this one, it's actually a really good analogy. Um, the potential energy is the water in the reservoir. The water in the reservoir, which is just there waiting to do work. It has potential energy because it's up high. It's higher than where it's going to be later, which is lower, and it will get down there due to gravity. So it will be spontaneous. But at the moment, that water here, has potential energy. Yeah. So chemical energy is really the energy of bonds. It's potential energy stored in bonds. Is it easy or hard to break those bonds? And that depends on how much energy you get out of the situation. Electromagnetic energy, and you will need to write these notes down because these notes don't get saved. So do write these notes down. Electromagnetic energy is kinetic energy of photons or waves, such as light, Light is a kind of energy. Infrared, infrared radiation, which really is just the heat that you give off of your body, for example, can be detected by infrared detectors. Um, Ultraviolet radiation, X-rays, those are all electromagnetic energy. So this is how a dam works. You've got your reservoir, and that water is high up. So water flows downhill absolutely spontaneously because of gravity. Yeah. So under the dam is a tunnel known as a penstock, and the water goes downhill through the penstock. And then that changes the potential energy of the water to kinetic energy of the movement of the water. And that movement is capable of turning this turbine, which causes a generator to generate electricity. So that's where the energy comes from. So we've converted energy from one form to another. We've converted that kinetic energy to electrochemical energy. So this idea of spontaneity is actually quite important. So because spontaneous things don't need energy input, they just happen spontaneously. So this diver up here has more potential energy up there than if he or she were down in the water swimming or just floating, I guess. Yeah, so the spontaneous part of this is that the diver dives into the water, and that is a spontaneous thing. So I really like this image or these images here because they show that things that are less stable have more free energy. So if the guy on the diving board is less stable, that person is more likely to fall off and release that energy. So less stable things have a greater work capacity or more energy. Now we're looking at the term free energy. That is the energy available in the cell to do work. Free energy is energy available to do work. Yeah. And in these three situations, the person on the diving board, these molecules that have been put into a solution, and this sugar molecule, they are all relatively unstable. So the person is relatively unstable, he'll just fall spontaneously. When you put, say, a dye into a petri dish of water, that might be what these molecules are, they're not going to just stay at the edge of the petri dish. They're going to diffuse spontaneously throughout the water. With a chemical reaction, a large molecule is more unstable than smaller molecules. So this is a large molecule, probably glucose. This is water and carbon dioxide. And so these small molecules, they hold the electrons quite tightly to them. So they're more stable. The large molecule tends to be a little more wavery, doesn't hold the electrons so tightly to itself. So those bonds of this large molecule are easier to break than these small molecules. Yeah, so in this way, we've gone spontaneously from a higher state of energy to a lower state of energy. So down in these states down here, there's less free energy, but they're more stable in that way, but have less work capacity. So those are the kinds of things to remember. And we want to know, well, in our bodies, we are constantly hydrolyzing or breaking down molecules that we eat. And we're constantly synthesizing them. When we break them down, that's spontaneous. When we build them up, that requires energy. And we can put those together which is neat. So we can use the energy we get from breaking stuff down to building other things up. A lot of um, chemical reactions are paired reactions. A chemical reaction is such that a bond is formed or broken. A chemical equation shows the reactants being changed into the products. There's different classes. Decomposition reactions, they are, as we just said, energy releasing. There are synthesis reactions. Well, they require energy, as you could imagine. Exchange reactions are both. Generally, they are both energy releasing and energy requiring. So they happen together, like reduction and oxidation reactions, for example, redox reactions. A decomposition reaction, we should say this also, is spontaneous. It releases energy for work in other places. It's also known as an exergonic reaction. Synthesis reactions are not spontaneous. They require energy input, and they are known as endergonic reactions. A decomposition reaction may be a large molecule, something you've eaten, some starches, broken down into simpler ones. In this case, it's starch, and it's broken down into glucose molecules. And we use the glucose molecules in cellular respiration. This kind of reaction, let me ask you, does this kind of reaction release energy or take energy up? And you can type that in the chat. A decomposition reaction, does it release energy? Yes. Good. Yes, releases energy. A synthesis reaction is the requirement of two or more smaller molecules being built into larger molecules. We're doing that all the time. We synthesize like 85%, for example, of our cholesterol. So two or more small molecules combine to form a larger one. In this case, they're amino acids, and amino acids form proteins or peptides. Is that an endergonic or an exergonic reaction? You can type that in the chat. Is a synthesis reaction exergonic or endergonic? Good. Yes, endergonic. An exchange reaction may very well be both, endergonic and exergonic. So we had some exchange reactions when we did that experiment with the raisins. It was an acid-base reaction. It was an exchange reaction. We got salts and water. Now my question to you is, what can increase reaction rates and why? So the basis for all reaction rates is molecular motion. We know that due to electrons whizzing about a nucleus with protons and neutrons, that our atoms and molecules in our universe are constantly moving. Yeah, if they're frozen, they're not moving very much, but if they're gas, they're moving quite a lot. And the basis for chemical reactions is molecular motion and that they collide. Yeah. So what increases that collision? What three things? What do you think this one indicates? And you can write that in the chat. What about this one or this one? Heat. Yeah, this shows heat. Higher temperatures increase reactions. Why? Well, heat causes molecules to move much more quickly. If they're moving more quickly, they're much more likely to collide. This indicates an increase in concentration. If you increase the concentration of the reactants, they will collide more often. So it will increase the rate of the chemical reactions. And this last one indicates an enzyme. So I should write this down, shouldn't I? I don't think I've got it. And the next one, no. Okay, so concentration of reactants. Indeed, if it's a reversible reaction, then the products increasing can move that reaction the other way. Temperature. And this last one indicates a catalyst in the form of an enzyme. So anything that increases the rate of reaction is a catalyst. But an enzyme is an organic catalyst. And they speed up the rates of reactions. So I'll put here increased temperature, increased concentration of reactants, enzyme presence. I'm going to put a little arrow here. All increase reaction rates. Yeah. So chemical reactions in the body are known collectively as metabolism, So there's two kinds, catabolism and anabolism. Catabolism is energy releasing or exergonic. We've learned that word already. Decomposition reactions. So you can think of them as decomposition, breaking things down. Catabolism, cats with claws. They break things down. That might be one way to remember. Anabolism is energy requiring or synthesis type of reaction. So the biggies, the large reactions that drive all life on Earth, the big one for catabolism is cellular respiration. That's our breaking down of glucose to get energy. Anabolism is photosynthesis in the large scheme of the world where energy comes from. Yeah. So the equation for cellular respiration is such: glucose plus oxygen. We are aerobic, so we require oxygen, 6 oxygen molecules, in fact. And that gives us water and something that we breathe out, which is, does anybody know? What do we breathe out? You can type that in the chat if you like. Yeah, CO2. 6, indeed, CO2. Photosynthesis takes that water and carbon dioxide from the atmosphere and makes sugar plus oxygen, 6 oxygen. So all our trees and plants and everything are taking up carbon dioxide and releasing oxygen into the atmosphere, which is great for us, of course. You might think, well, there's something missing here. Well, what then, if photosynthesis is energy requiring, what drives photosynthesis? Where does that energy come from? So you can type that in the chat if you like. It's going away today, by the way, because it might rain soon. So what drives photosynthesis? Yes, energy from the sun. So that requires energy. Cellular respiration just has this large glucose molecule that's kind of unstable, and oxygen, which is super reactive. Oxygen loves to drag electrons toward itself. That's why this whole system works. Yeah, and it releases energy. And the energy it releases is used to make ATP. So I think it's 36. So plus 36 ATP. Let's see, I'm going to write this up here. Plus. This drives the synthesis of ATP from adenosine diphosphate and inorganic phosphates into adenosine triphosphate. This is really fantastic, fantastic molecule that we use for energy for everything, muscle contraction, transport, breathing, you name it, we use it for that. ATP, adenosine triphosphate. And, and we're not really getting to that just yet. So we're going to talk about ATP later, but what's so neat about ATP is it looks like this. So you've got your adenine here, and you've got these phosphate groups, 3 of them, triphosphate. Well, the thing about phosphates is they all have a negative charge. And what is the effect of one negatively charged particle and another negatively charged particle? Do they attract each other or do they repel each other? Repel. And so we usually draw this as a squiggly line, meaning it's very unstable. And what do we know now about stability and instability is that something that's unstable is going to be spontaneously giving off energy or um, driving other reactions by releasing energy. Amazing. Organic molecules are carbon compounds and they're functional groups. So you may or may not have taken organic chemistry, but that's generally how it's defined. Carbon compounds, and some of the major ones are carbohydrates, lipids, proteins, nucleotides, and nucleic acids. Those are the biggies. Yeah. And these are what we catabolize for energy. So organic molecules are carbon molecules. And carbon is this really cool molecule. In that, carbon is, I should say atom, it makes these cool molecules because carbon has these 4 unpaired electrons in its outer shell. So it can make covalent bonds with 4 different things. Yeah, it's like the party animal of atoms. So now I'm just going to stop share and I'd like to show you a quick video about carbon.